Alright, here we're going to look at a comparator being used in an application called threshold detection. So this circuit you see is an example of a threshold detector where we're automatically controlling a furnace. So if you take a look at what we have here, here's our op amp without any feedback. So here's the comparator. In the inverting input we have a temperature sensor connected, which is giving us a DC input that will be 0.1 volt per degree Fahrenheit above 0 degrees Fahrenheit. So, you know, if it's 1 degree Fahrenheit, we get a tenth of a volt. If it's 10 degrees Fahrenheit, we have 1 volt, 20 degrees Fahrenheit, 20 volts, and so on. Then the output of the comparator goes to the input of a transistor switch circuit. Okay, so this is a BJT switch circuit. And here in the this part of the circuit between a source of plus V and this resistor RC is the furnace controller. So the way this works is that when the input voltage of the transistor switch, which is equal to the output voltage of the comparator, when it's equal to plus 5 volts, which is one of the possible values because that's our plus power source as you see here, well, that's going to make the node here C and the node here E a short. Okay, so CE would be a short, and if CE is a short to ground, well then there's a path for current to flow through the furnace controller and the furnace would be on. Okay, so furnace on. Okay, now when V0 is the other possible value, which is 0 volts ground. Alright, so we're assuming this is one of those op amps where you can ground the minus V input. Okay, so minus V is just grounded to make it 0 volts. Well, that would make the input to the transistor switch circuit also 0, which would make the collector to emitter, or the CE node, act like an open. And if it's acting like an open, there's no path for current to flow through the furnace, so the furnace would be off. Alright, so we're using the output of the comparator to determine when the furnace is on and when it's off. Now, to see how this works, first of all, this fixed source here, which is our reference voltage. Okay, remember a lot of times with comparators where your fixed voltages, that's called the reference voltage. And that, as you can see, is connected to the non-inverting input of the comparator. Well, in temperature, okay, using our temperature sensor characteristic here of a tenth of a volt per degree Fahrenheit, well, 6.8 volts, because of this sensor, corresponds to 68 degrees Fahrenheit. Alright, so you see this fixed voltage here, this is referred to as the threshold, because this is going to determine, this value here is going to determine when the output of the comparator changes from plus V to minus V or vice versa. Okay, because on one side of this reference we'll have one value of V out, on the other side of this reference we'll have the other value of V out. Okay, so let's see specifically what we get here. So let's say, you know, first let's say, what if our temperature is less than 68 degrees Fahrenheit? Okay, so that would correspond to the voltage that we have on this inverting input. And we'll call this V, just VS for sensor. Yeah. Okay, so that would mean that VS would be less than 6.8 volts. Okay, so this means that the voltage on the non-inverting input, that I'll call VP, okay, which is the same as V reference, well, that voltage would be greater than VS, which is the voltage on the inverting input. right? Vn, same as Vn. Okay, and when the voltage on the non-inverting input Vp is greater than the voltage on the inverting input Vn, like we talked about before, well, the output V0, the comparator, is going to be plus V, right? It's going to be the plus power source here, which would be 5 volts. Okay, and as we said over here, when V0 is 5 volts, that makes the collector to emitter act like it's short. Current's going to flow through the furnace, and the furnace is going to be on. Okay, which is a good thing, because if the temperature is less than 68 degrees Fahrenheit, you probably want to warm up your place. Okay, so that makes sense. All right, well now, now if our temperature is greater than 68 degrees Fahrenheit, well, it should make sense to you based on our discussion of a comparator, right? How a comparator works. That now when this other input voltage, when Vn is greater than Vp, that's when you're going to get the other possible value of V out, which is the minus V source, which here is ground. Okay, so now the output of the comparator is going to be 0 volts. So that's going to turn this transistor switch from collector to emitter off, making it open. No current's going to flow through the furnace, and the furnace is going to be off. So you see, we're using this comparator to control when the furnace turns on and off based on the input conditions that are based on temperature, right? It's just these voltages represent temperature levels. Now, just some practical tidbits before we end this video. One is that in a practical circuit, it's unlikely that this reference voltage would be a whole nother source, because you already have a source that's applying the power to the op amp. So usually it's not cost effective to have, a whole nother source over here for your reference voltage. So in a practical circuit, we use a component that under the right conditions acts like a voltage source, and that's a Zener diode. So this 6.8 volt reference in a, chances are in a real circuit like this, it's going to be a Zener diode that's operated in the reverse bias condition, and it's going to act like a 6.8 volt source. So you'd use a Zener diode with a VZ of 6.8 volts. Another thing that you can do here is you could take out this source and instead put in this, oops, instead, for our reference voltage, we could put a resistance we could put a resistor along with the variable resistance connected to the non-inverting input. Now remember, comparators, while they don't have a virtual short because the voltage across the inputs is not equal to 0, it's equal to the difference of Vp and Vn. However, there still is 0 current ideally at the inputs of a comparator. So you see, when I connect two resistors like this up to the non-inverting input, since no current is going to the non-inverting input, all this current would just stay through the resistors. So I have a series circuit of these two resistors, and my V reference would be across this variable resistance. So as I vary the resistor, I'm changing how this plus V voltage splits up amongst these two series resistors, and that varied V reference is now going to determine the threshold of which determines when the furnace turns on and off. So you see, this would be a thermostat, that just using a couple of resistors like this where one of the resistors is variable, that variable resistor would be called a rheostat. That's how we get a thermostat in this type of problem. Okay, so that was a couple of tidbits of important information. Another one is that, and we talked about this a little bit when we were going over the basics of a comparator, and that's when the input voltages of a comparator are close to each other. Okay, when Vp and Vn are essentially equal. And remember, it's hard for voltages to be exactly equal for any significant amount of time, mainly due to thermal effects, that you'll get fluctuation in voltage over time. And again, if you've taken an EE lab, you've seen that firsthand. So when Vp and Vn are close together and they hover around each other's value, that's when your output of your comparator is going to become unstable. It's going to oscillate between these two outputs of plus V and minus V. So see, that's a drawback of a comparator circuit, is that you have this instability point. And I just want to make a little graph of this. Okay, a graph of V out versus V in for a comparator. So we'll label it Vs here, because we called our input here Vs. Well, if this vertical line here is our reference voltage, right? When our Vs is less than the reference voltage, that's when the furnace is going to be on, right? So this is furnace on. And when our input voltage is more than the reference, right, that's when we're going to have the furnace off. Okay, and you see it's this vertical right here at V reference, right? You could be going either direction here depending on how the temperature is changing, right? That, you know, here the furnace is off, but then once the temperature gets to 68 degrees Fahrenheit, or once the input voltage gets to the 6.8 volts of the V reference, well, that's when the output is going to change, so that now the furnace is off. But then if it immediately cools, the furnace will turn back on. And then if it gets a little warmer right after that, well, the furnace is going to turn off. So you see this right here is what marks the instability point, right? It's when your input voltage is hovering around the reference voltage, that on one side of that reference voltage you're going to get one value of V out, which in this case is going to turn the furnace on, and on the other side of that reference voltage you're going to get the other value of V out, which is going to turn the furnace off. And you see, it's not good for a furnace, or any mechanical device for that matter, to be quickly turned on and off like that. You can actually damage the furnace. So you see, in an application like this, the instability point at V0 is not desirable. And in the next video we're going to talk about a circuit called a Schmidt trigger that you can use to alleviate this problem. But you know, in some other applications, the fact that you have this instability point is not an issue. For example, you know, let's say instead of a temperature sensor we used a light sensor, and then instead of controlling a furnace we were controlling some sort of lighting device. In fact, you know, many of you, I'm sure, have gone to parking lots where the parking lot lights come on at dusk. And if you've ever been there where those lights first come on when it just gets dark enough to activate them, well, you might have noticed that they don't come on right away and stay on. A lot of times what happens is that they'll flicker. They'll flicker until it becomes dark enough where they'll stay on and not flicker anymore. Well, during the time that they're flickering, I mean, that's what you're seeing. You're seeing the output of a comparator circuit like this at the unstable point. That's what's called the flickering, as the output goes on and off, and current flows through the lamp and then doesn't, and that's what causes the flickering. And in that application, you don't care. You don't care that the lights flicker a little bit before they come on and stay on. So a comparator would be fine for that application. Okay, but in applications where that instability at V0 due to the inputs being close together in value, when that is a problem, there's something you can do, and that something's called a Schmidt trigger, which we're going to talk about in the next video.